Now let's design Google Drive or any similar service like it, like Dropbox or Microsoft OneDrive, but basically a cloud storage solution for users to store files. And to quickly go over the background, with a service like Google Drive, you can upload files, you can download those files, of course, you can remove or delete those files. This is kind of the basic core functionality, but beyond this, you can do a lot more. You can definitely edit files as well. Like if you had a Google Doc stored on your Google Drive, you could definitely edit that file because it's just a regular like text file. You can share files as well with other people and kind of manage the permissions for every file, like who's allowed to download the file, who's allowed to like edit the file, remove the file, things like that. You can also store things in a hierarchy with folders to actually like organize and group your content. Now this seems simple enough, but as we're going to notice, the problems that we run into are going to be those of scale, the scale that Google Drive has to handle. So in terms of functional requirements, let's say that we want to mainly focus on the upload and download case, and of course removing files as well. We'll talk a tiny bit about editing, but this is actually the most complicated among all of these features, being able to kind of edit a file, as we're going to see. But mainly what's in scope is these three. We're not going to kind of focus on like the permissions aspect of it, like sharing files, but we will be supporting folders and organizing things like in a hierarchy. In terms of non-functional requirements, let's say that we have about 200 million total users, which is probably, to be honest, small for Google Drive. There's probably over like a billion. But in terms of daily active users, let's say that we have something like 50 million daily active users, and every single user is going to be given 15 gigabytes of free storage, which is exactly what Google Drive offers. Now, of course, there's going to be a subset of the users that actually pay for additional storage. Like some people might be paying for a terabyte of data, or, even maybe a petabyte, or maybe even, 10 terabytes or 100 terabytes. But since Google Drive is kind of supposed to be a user-friendly product, like for consumers, not for like developers necessarily, probably people aren't going to be storing like petabytes of data on here. And since it's going to be such a small subset of users that are storing more than 15 gigabytes, most likely, we can kind of just assume that the average user is going to have 15 gigabytes. And in addition, most people aren't actually going to be taking up all 15 gigabytes. But then when you get to the total amount of storage that we're going to be taking up with this, remember 50 million is 50 and then 3 zeros and then 3 more zeros. And when you multiply, 15 gigabytes by 1,000, we get 15 terabytes. When you multiply that by 1,000 again, we get 15 petabytes. And actually 50 million is actually the daily active users. The total users is probably what we care more about in terms of the total storage. So let me scratch this 50 and replace it with a 200. So we actually have 200 million users. Our math is still the same up until this point though, because we basically multiplied this by 1,000,000 and we got 15 petabytes. Now multiply this by 200 and we will get 1,500 plus 1,500, which is going to be 3,000 petabytes of data, which basically in conclusion is a very, very large amount of data. That's the main conclusion here. Also 15 petabytes is actually 3 exabytes, but I personally just remember the units up to peta, and you can see if you just write it out as 3,000, you don't even have to know the units beyond this. But what's also worth mentioning that every file that somebody uploads to their 15 gigabytes of storage, we really cannot allow that data to be deleted. So it's pretty safe to assume that every file that's going to be uploaded is going to need to be replicated, and most likely not just in a single zone, because what if there's a natural disaster and one of the data centers is destroyed for some reason? We probably want to replicate this around the world multiple times, at least 3 times, but maybe even more than that. So basically 3,000 petabytes is a lot, but we're probably going to be needing to store even more than that. So in conclusion, a massive amount of data. Also, in terms of throughput, let's say that the average person uploads 2 files per day. And on average, maybe each one is like 10 megabytes each, but that might be even higher, especially if they're doing something like a text file or a PDF. If it's like an image, maybe 10 megabytes are like videos and things like that. And let's say kind of the read to write ratio is 2:1. So there's going to be 2 reads for every write. So every file that's uploaded, let's say there's 2 files per day, 10 megabytes each, there's going to be 4 files that are downloaded, 10 megabytes per each. Now, in the context of Google Drive, throughput is probably not the biggest problem here. Even latency isn't necessarily the biggest problem if it takes, a couple extra seconds for a file to download. That's really not what we're trying to get out here. This isn't like we're watching YouTube videos where you want to have a really really user-friendly experience. What's probably most important in the context of Google Drive is that, first of all, it's always available. You'd never want to try uploading or downloading a file, and it could be a really important file that you're trying to download. You would never want it to not be available to you, because at that point, you'd probably not even feel safe uploading data to Google Drive. You'd rather just store it on your computer. So availability is probably the biggest, most important requirement here non-functionally, in addition to reliability, because obviously you could upload a file and then one day it's just not there anymore. That would be a problem. Now let's get into the high level design. And in this case, let's actually start with kind of the data model and how we're going to be storing the data. We know, of course, we're going to be storing two things: the actual files themselves, and then probably a lot of metadata, things like user metadata, as well as metadata about these files. Now, because these files could be anything, if it's just a text file like a string, technically we could store that in a database if we wanted to, like a relational database or a NoSQL database. But we could obviously be having images, videos, like pretty much any format of file. So we need something much more flexible than that. Now, the metadata, of course, can just go in a database, whether it's SQL or NoSQL, probably doesn't matter. I would probably just go with NoSQL because it's going to be pretty straightforward. We're probably not going to be needing a lot of joins. It's going to be mainly, a key value store. That's how we're going to be using it. So, this could be something like MongoDB or AWS DynamoDB. But mainly, this is probably not going to be the bottleneck. We know we're going to be storing massive amounts of data, and that massive amount of data is probably not going to be stored here. It's not going to be the metadata. It's going to be the files itself. So how do we want to store these files? We're probably not going to be using like a regular database, but we do need this data to be persistent. So the two options that might come to mind for you is a distributed file system, something like Hadoop distributed file system. And another option would be an object store. Now let's briefly compare these two. I think they're both viable options as long as you can kind of defend your design decisions. But this is kind of one of the major decisions when it comes to Google Drive, of course, how we're actually storing the files. Now let's briefly compare a file system to an object store. First of all, a file system, just like on your local computer, is stored in a hierarchy. So going back to data structures and algorithms, which, believe it or not, don't go away, a file system can be kind of thought as a tree, not necessarily a binary tree, because you can have a folder, like let's say this is your root folder, and then here you can have some other folders like ABC, and maybe this is where your binaries are stored, bin, and some others. And then inside of these, maybe you do have some files like x.txt and things like that. And here we could actually have another folder, and that could have some files in it as well. Basically, file systems store things in a hierarchy, and you can kind of visualize them like that. But in reality, they're also stored similar to this on your actual disk. Like on your computer, you have some persistent storage. That data is stored, organized in such a way like this, where if you're in a folder, you can go through all of its children pretty easily. It's well organized. And since Google Drive supports folders, you would think that this hierarchy is going to be helpful, which it would be. And one problem would be actually scaling this file system. Like I said, we could use a distributed file system where we have multiple nodes kind of storing all that information and we scale it. Now, this can definitely be much more complicated. That's kind of the downside compared to an object store, and it's less scalable. And with an object store, the scalability comes kind of for free, especially if we use like an external service like AWS S3 or Google Cloud Storage or Azure, which I think has Blob Store. Now, another benefit of a file system is that you can actually modify files. Like you can actually edit a file. You can't really do that in an object store. Files are immutable. You can delete a file and then create a new one, but you can't really edit an existing file. But since we're not really focusing on editing files, that won't be super important for us to actually like go in depth into. And there are, potential workarounds, especially if we were talking about small like text-based files. You could just kind of load the file and then kind of store it in memory somewhere and then edit it like that. You don't actually have to edit the file on the object store. And if it's something like a video or an image, maybe we wouldn't even support editing it in the first place. Now, just to kind of briefly wrap this up, an object store is more of a flat data structure. Even though in AWS S3 you can have folders, those folders are actually an illusion. They are just in the name. So like you could have some files like in my bin directory, I have some file like A, and then in the same directory bin, I have a file called B. If you opened up the bin folder in AWS S3 or something, you'd see these two files. You'd see the file A and you'd see the file B, but those folders are actually just in the name. Like the way that kind of logic works is it just sees, well, every file that has a prefix like bin, I'm going to show all of those files now once you kind of click that directory. But in reality, these are stored in a flat data structure. There's no hierarchy. It can kind of be thought as a hash map where the ID, or kind of the unique name of every file, is like the identifier. And then when you use that name, you kind of see the individual file. You can download the individual file. So we will be going with an object store, and not to mention object stores kind of provide that reliability and availability for us, like multi-region replication and availability and all that stuff. So at a high level, we will have application servers. So if a user uploads a file, they will hit the application server. Of course, we could, load balance this. It wouldn't really matter which application server the user hit, because ultimately the application server is going to just upload the file and store it in an object store. Now, as a file is uploaded, we also need to kind of store metadata about that file. Like we need to definitely have a reference to that file, because when a user now wants to read a file, they'll be hitting the application server. We'll be reading which file they wanted to read. We'll get the metadata for it, and we'll return like the actual file itself from object store to the user. And we would most likely just need a regular KV store. Something like a NoSQL database would probably work. Now we can definitely have a caching layer as well. I mean, why not? But most likely it's not like there's going to be a single file that's going to have that many reads. So caching isn't really the most significant part of this architecture, at least in the context of this problem. Now let's start going over some of the details. I mean, the good thing is at a high level, this is pretty straightforward, but there's a lot of details we could possibly discuss. One of the first things is typically in object storage, we've talked about like media files like images and videos, and generally you don't really need permission control on those, especially if you're going to be distributing them over like a CDN network. In this case, since these are kind of personal files that people are storing, they expect that only they will have access to them. And even though we're not talking about like sharing files and permissions, I think it's worth mentioning that you can kind of configure an object store to not be accessible publicly. Like typically a user's browser would be making the request for like an image that's stored on an object store, which is maybe distributed on like a CDN. But in this case, we would probably want to restrict access to our object store only to our own app servers. So if a user is trying to access a file, our app server will be able to determine if they have access to it in the first place, probably using like our KV store, some authentication token from the user, and only then would it directly read the file and then respond with the file. Now we talked about having such a massive amount of data that we're actually going to be storing for the files. While an object store can probably still handle the scale, like S3 could probably handle the scale, but it would cost a lot of money, especially if we're giving this away for free. So one technique that you may not be aware of is called block level storage. What it does is as a user uploads a file, that file is actually broken up into these blocks, and the block size is typically fixed. It could be on the order of like megabytes. Something like 4 megabytes might be reasonable. So every file is going to be broken up into 4 megabyte chunks, and those chunks are going to be stored in object storage. And so when a user now wants to actually read that same file, we have to reassemble it using these smaller blocks. And how we would know to reassemble it and how to do so would probably be based on data that we're storing in our KV store. So we could have a document in here saying that this is my file name ABC, and it belongs to this particular user. So we'd have like a user ID, and then we'd have like the references to all of the blocks, and then we could reassemble an individual file using all of those blocks. Now, why are we doing it this way? Well, one advantage to this, and the biggest one that I wanted to point out, is that if we break data up into smaller blocks, it's possible for us to do something called deduplication. That means, for example, for an individual user, if they're uploading multiple files and we're breaking every file up into blocks, but we notice that for one file, one of the blocks is identical to another file's block as well. And since when a user fetches a file, all we really need to do is reassemble that file. So if we ever notice any duplicate blocks, blocks for a single user, we will not store that. So maybe this is a file that a user is trying to upload, but we see that this block has already actually been stored in our object store and we have a reference to it. So we would not restore this data. Maybe it would save us like 4 megabytes in this example, but on like a higher scale, this would probably save us more data if some users are duplicating a lot of data. Now, what would be even better is instead of doing this on a user level, we could do this on a global level for every single user. That means if I'm uploading a file that somebody else has already uploaded to Google Drive, we don't really need to store the exact same file multiple times. And also we don't need to store the same block multiple times either. Even if the entire file is not identical to another file, if blocks are identical, we don't need to duplicate any blocks. So doing this on a global level would probably save us a lot of storage, which most importantly would save us a lot of money from the perspective of Google Drive. Now, without block level storage, when a user deletes a file, we probably would have deleted all of the individual blocks. We would have deleted the entire file. But if we're doing global deduplication, we probably don't ever want to delete any block. We probably don't need to because it could be used by another user. So if we delete every single block, but one of these blocks was actually referenced by another user's file, we wouldn't want to delete that because then we would be able to reassemble their file. Now it's kind of hard to quantify exactly how much space this would save us, but at a high level, this is kind of a technique that's actually used in industry. This is not something that I just made up. Now, also worth mentioning, if we did this on a user level, not on a global level, then maybe for every single block in our KV store, we would kind of store a count for every single block. Like if one block is stored 2 times and then a user deletes a file, then we kind of decrement that count. Now that block is only being stored 1 time. And if it's being stored 0 times, at that point, we probably can delete it from our object store. Now, an important question is, how do you actually know if a block is being stored multiple times? You would, in the worst case, have to go through the entire object store and actually read the content of every single block. Is there an easier way to do so? Well, maybe if we can create an ID based on the content of every single block, a unique ID, so that if another user uploads the same block in a different file, when we create the ID from that block, we get the same ID, and then we would know it's already been stored because that ID is probably being stored in our KV store, and that ID is what's being used to reference the block in our object store. And again, if I was interviewing you, this is kind of all I would personally expect you to come up with and not know like the actual details, but this is also kind of something that's done in industry. It's called content addressable storage. So we basically take the content of something and then use the content to create an address so we can kind of identify duplicates easier that way, and we can kind of easily search for that individual block. This is probably how we would want to store a reference to every block in our KV store anyway. And by the way, this is also kind of a reason why editing these blocks is going to be tricky and why we're not really focusing on that, because if you create a hash based on the content of something, but then you edit the content, then don't you have to recreate a hash? Well, if you edit that block, what if you kind of mess up somebody else's data? There's a lot of kind of open questions that come about this. That's kind of why these blocks are immutable and object storage in general is immutable. Now, another thing worth mentioning, and this is just kind of a small detail, is kind of with this block level storage deduplication, if somebody is uploading a file and then that upload kind of messes up halfway through, like, you were uploading 10 gigabytes, but only 5 gigabytes were uploaded, and then you try to upload the next 5 gigabytes. Well, the good thing is, since we're, breaking everything up into blocks, we would notice that those first 5 gigabytes are already uploaded. We would not need to restore those in our object store, and we'd figure that out by our app server reading from the KV store. Now, a question we haven't addressed yet is, what about folders? Should we store the folders in object storage? Or alternatively, we don't actually have to store them here at all because they don't really take up any like data blocks or anything like that. We can kind of just store the metadata for all our folders in the KV store, and that's probably what I would prefer. So we can have that hierarchy in our KV store. We can, for every single folder, have a reference to all of its children, and of course every folder is going to be owned by a user. Like there's no data blocks or deduplication in terms of folders or anything like that, and every folder would have like a reference to every file that the user is storing. That's all stored here, and then that file will have information or references to all the data blocks, and that's how we can build those individual files. Now, what about going from a file back up to the folder? Well, maybe every single file document has a reference to the folder. So kind of having two-way pointers, a pointer from the folder to the file and from the file to the folder. And we can have nested folders as well. Having pointers, I think, kind of addresses this problem. And another thing, I mentioned that when a file is deleted from Object Store, we actually never delete the data blocks from the Object Store because technically they could still be referenced by some other users. And for us to determine if a block is referenced by any user, we would, in the worst case, potentially have to scan through the entire KV store. So every time a user deletes a file, we don't really want to have to do all of that work. But we could still have a separate service over here, something like a garbage collection service, which doesn't run like synchronously every time a request is made, but asynchronously, let's say maybe every 1 hour or periodically, it will scan through the KV store, find any data blocks that are not referenced anymore, and then delete all of those data blocks from the object storage. This is kind of another optimization to save space. We kind of get the best of both worlds with having like deduplication, but also getting rid of data blocks that are no longer being used. Now, another possible optimization we could make when it comes to reliability, or at least we could describe further, is we talked about we would have like a load balancer here, most likely before our application server. Now, what happens if the load balancer goes down? Well, ideally, we'd have like another load balancer to take its place and then redirect user traffic there. But how do you know when a load balancer goes down? Well, there's this concept of a heartbeat. What the load balancer that's active would do is it would continuously send a heartbeat to some data store. A common one is called Zookeeper. It's not exactly like a database. It's a highly available key value source, similar to what we're using here. But here we'd be using something like DynamoDB. But whereas Zookeeper is more commonly used to coordinate distributed systems, it's highly available, it's highly fault tolerant, and it's a specialized solution for using heartbeats and coordinating a lot of distributed systems, including Hadoop, Spark, Kafka. We're just talking about the high level here because this is kind of a service you would probably want to use with your load balancer to know if the load balancer goes down. And the backup load balancer would be reading from Zookeeper to see, is that first load balancer sending a heartbeat? Maybe if 10 seconds go by and there isn't any heartbeat, that means we can assume that the first load balancer went down. Therefore, we should start directing all of our traffic to a second load balancer. There are definitely other things we could have explored. One interesting question would be how you would want to handle being able to edit files, because since you can't edit blocks and objects and files on an object store, we would probably need to handle that logic elsewhere and then maybe add new blocks for new data that we wrote to a file. But we definitely covered a lot of the most important questions with designing a service like Google Drive, mostly how we would actually store the data in an efficient way.